Hello everyone, my name is Rani. My roll number is 22955A0515. I am studying at Institute of Aeronautical Engineering. So today I am going to give presentation on existential quantifier with example. So contents are quantifiers, existential quantifier, forms, example of existential quantifier, and conclusion. So let's see what is quantifier. Quantifier is used to quantify the variable of predicates. It contains a formula, which is a type of statement whose truth values may depend on values of some variables. So, so, so to quantify the variables of predicates, we are using quantify. So, like to prove the truth values may depend on values of some variables, like it is a number of saying that number of things, like some, all, in such a way. When we assign a fixed value to a predicate, then it becomes a preposition. In another way, we can say that if we quantify the predicate, then the predicate will become a preposition. So if we quantify the predicate statement, then that statement will become a preposition. So quantify is a type of word which refers to quantifies like all or some. So quantify is a type of word which refers to quantifies like all or some. There are many types of quantifiers. There are universal quantifiers and existential quantifiers. So the combinations of quantifiers and predicate the statement will be formed, which is to say that some of things. It also shows that for all possible values or for some values in the universe of disclosure, the predicate is true or not. So the statement is true or not. To show that we are using quantifiers, which is universal quantifier and existential quantifier. So let's see a simple example. If there is a x that is less than 5 and equal to 5 and x is greater than 3. X is less than or equals to 5 and x is greater than 3. This statement is false for x is equals to 6. So this statement is false for x is equals to 6 and true for x is equals to 4. Here, if the x is 6, if we think x is 6, 6 is less than or equals to 5. No, 6 is greater than equals to 5. And 6 is greater than 3. Yes, it is greater than 3. But it is not less than or equals to 5. So it is false. And true for x is equals to 4. If we check 4, 4 is less than or equals to 5. Yes, 4 is less than or equals to 5. And x is greater than 4, which is like 4 is greater than 3, right? Now this statement is true for the x is equals to 4. Now if we will compare the above statement with the following statement, for every x is less than or equals to 5 and x is greater than 3, we are saying that for every of x should less than or equals to 5 and greater than x is greater than 3. Here we are giving the condition that if for every of x we are taking number of x like 1 2 3 in such a way, right? For every of x it should less than or equals to 5. It may be like any of the number, but it should less than or equals to 5 and x is greater than 3. This statement is definitely false. Now we will again define a statement, because every number, if we took 1 2 3 4, yes I said, but that all is not satisfied with the condition, that is x is greater than 5 and x is greater than 3. So for some numbers it is false, right? That is like 6 7 8, it is false for that. So it only accepts x is equals to 4. If we substitute, let's take this example more detailedly. If we take x is equals to 1, yes, 1 is less than or equals to 5 and x is greater than 3, it is false. If we take 2, 2 is less than or equals to 5, yes, true, but x is greater than 3. No, it is not possible, 2 is not greater than 3. And if we take 3, 3 is less than or equals to 5, yes, and x is greater than 3. No, 3 is greater than 3, no. So if we take 4, x is 4 is less than or equals to 5 is true, and 4 is greater than 3, yes, it is satisfying. And if we take 5 is okay, it is satisfying, and x is 5 is greater than 3. So here for 4 and 5, 4 and 5 is accepting it. If we take 6, 6 is less than equal to 5. No, 6 is not equal to less than or equals to 5. And greater than 6 is greater than 3. Yes, it is greater than 3, but it is not satisfied is the first condition, that is less than or equals to 5. So here 4 and 5 are only going to accept this statement. So only two of them. There are 9, so there are 9 digits, but out of them only two of them are satisfying the statements. So not every of x is going to not every of x, not 1 2 3 4 5 6 7 8, all of them are not going to accept the statements. So they will be not coming for every of x. X is less than or 5 and x is greater than 3, only two of them accepting. So we should write like this statement, that is, there exists an x such that x is less than 5 and x is greater than 3. It says that sum of numbers of x such that x is greater than 5 and x is less than 5 and x is greater than 3. So this statement is definitely true. The phrase there exists an x such that is known as existential quantifier, and for every x phrase is known as universal quantifier. The variable in a formula cannot be simply true or false unless we bound these variables by using the quantifiers. So let's see the more detail about existential quantifier. The existential quantifier symbols is denoted by the E, which is reverse of E, capital E, which means there exist. Suppose P of x is used to indicate predicate. So predicate is like some action, and D is used to indicate the domain of x, that is x. D is used to indicate the x. The existential statement will be in the form of there is exist x. There exists x belongs to domain of x such that P of x. So there exists a x belongs to domain of x belongs to x such that P of x. P of x is nothing but predicate of x. The main purpose of an existential statement is to form a preposition. So the main purpose of existential statement is to form a preposition. The sentence there exists x, P of x will be true if and only if P of x is true for at least one x in D. So this is true if for at least one x in D. The statement x there exists x belongs to there exists x, P of x will be false if only if P of x is false for all x in D. So this is false for all x in D if there is at least one x in D. If there like a sum of x's, like sum of numbers has we took before the example, like x is less than 5 and greater than 3, there are only two numbers which satisfy the condition, so we take there exist. If there every number satisfies that statement, then we will keep for every of x. So here it is saying for at least one x in D is satisfying that statement. So forms, so they like we use some keywords to show the sentence, to show the statement. There exists on x such that P of x, or for some x P of x, or we can write we can find an x such that, or we can write also there is some x such that P of x, or there is at least one x such that P of x. So examples, let's see the examples. Suppose P of x contains a statement x is greater than 4. Okay, now we will find the truth values of this statement. X is greater than 4. He given the P of x is greater than 4. Now we will find the truth values of this statement. This statement is false for all real numbers which is less than 4. So 3 is not greater than 4, 2 is not greater than 4, 1 is not greater than 4, which are real numbers less than 4, and true for all real numbers which are greater than 4. This statement is false for x is equals to 6 and true for x is equals to 4. Now we will compare the above statement with the following statement. So extension of x P of x is true. So in such a way you have to do. So extension quantifier p of x is true. Like here x is greater than 4, so some of them may not exist, so here less than 4 are not accepting, but greater than 4 are accepting, so that we are using there exists x, p of x is true. There exists at least x such that p of x is true. So let's see the another example. There is a fox that is faster than all snails. Okay, we are taking there we are taking snail as y, and exists there exists a there exists a fox. Here taking fox as f and snail as s and p as x comma y. Okay, means we are comparing, right, faster, so p of x comma y. So there exists a fox for x such that, for here the question is given that there is a fox that is faster than all snails. We are comparing the foxes with the snails. There exists a fox, there may be a sum of fox. There exists a fox such that for any snail a y. Here they said that in the statement they're given there is a fox that is faster than all in the sense universe quantifier. If it is universe quantifier, we should use for any, for all, right? So here we are using for any snail y. X is faster than, x is faster. So there is a fox, it is like only one fox that is faster than all snails. If we convert that into the statement, there exists a fox x such that for any snail y, x is faster, x is faster. So here it is saying in such a way, there exists x belongs to f, there is exists belongs there is there exists x belongs to f, and for any y belongs to s, for any y belongs to s in the sense snail, p of x comma y, if x comma y is x is greater than. So if we convert it into a statement, then this will come like there exists x belongs to f, which is fox, there exists a x belongs to f, which is fox, and for any y belongs to s, for every snail, p of x comma y. And let's see the another example. There exists x belongs to d and p of x. There exists x belongs to domain d such that p of x is true. Means some of them are true. It's saying some of them are true. Let's another example. So yeah, conclusion here. The phrase there exists an x such that is called an existential quantifier and is denoted by capital E, reverse of capital E, x. A formula that contains variables is not simply true or false unless each of these variables is bound by a quantifier. So depending on how many variables, how many things it is having, like there exist or some of them or all, in such a way. The existential quantifier symbolized E expresses that the formula following holds for some, at least one value of that quantified variable. So it only specifies some of them, not for all. If it is not, it is for all, it is universe quantifier. If there is some of them, then it is exponential quantifier. So thank you. I'm going to complete my presentation.